Okay, so we're going to talk a little bit about wavelength and frequency in this video and speed of light. So the first thing to know about light is that light is energy, okay? Light is not matter. It's made out of massless particles called photons. So light is one of the few things that, is actually not matter. It has no mass, right? We said that matter has to have mass and volume. Light does not have mass. Light does not have volume. So light is not matter. But light is energy. Okay, photons have energy. We just calculated the energy of a particular photon that was in yellow light. Okay, so light, another name for it, is, as I mentioned before, is electromagnetic radiation, and all light travels at about 3.0 times 10 to the 8th meters per second. Thousands of different experiments have shown this to be true. This is when light is traveling through a vacuum, so when there's nothing else, so like in outer space. Basically the same value, slightly slower in air. Light, just so you know, this is getting more into physics stuff, but light will travel at different speeds depending on what medium it is in. So light will travel at a different speed in water, right? Light is, we'll talk about this, it has wave-like properties. This particle called a photon, I'm calling it a particle, but it also has wave-like particle properties. So light is both a wave and a particle. And certain experiments, it shows up as, it looks more particle-like, and certain experiments, it looks more wave-like. This is one of these strange things just about light, and it's just the way it is. It's, again, bizarre stuff, and amazing really things about the universe. But anyway, what I was saying is, like, in water, light will travel slower, and this will cause what's called refraction. You don't have to worry about this for the exam or anything, just telling you this. If you put a pencil in a glass of water, right, you'll notice that that pencil looks bent to your eyes, and that's because the light is refracting. It's going at a different speed. The same reason why, your voice sounds weird underwater. Sound waves are traveling at a different speed in water. So, but the key thing is, all light, doesn't matter what wavelength it is, what energy it is, in a vacuum travels at c, right, which is this constant for the speed of light, about 3.0 times 10 to the 8th, 300,000 meters per second. So that's the first thing. With wavelength, we use the term, the Greek letter lambda, and that's the distance, defined as the distance between consecutive peaks. So, so it's going to be the distance between here and here. That's the wavelength. This would have a relatively long wavelength, pretending to be red light. This is a graphic pretending to be blue light, right? And the distance, the wavelength between the peaks is shorter. You could also measure the distance between the troughs, the bottoms. So from bottom to bottom, that's the same as from top to top. So those are both wavelengths. Those are equal. And we use units of meter. For visible light, we like to use nanometers because visible light ranges from 400 nanometers for violet light to red light, which is around 700, 750 nanometers, depending upon how good your eyes are. So frequency is the number of cycles that pass through a point in 1 second. So it's in units of per second, cycles per second. We also call that hertz, abbreviated as Hz. Frequency, remember, is given this nu, Greek letter nu. And so here would be an example of, all right, every 2 seconds, right? Every half a cycle second, every 2 seconds, a new peak is hitting this green line, right? Whereas on the bottom here, every second a peak is hitting the green line. So that's what frequency is. Bottom, we'd say, has high frequency relative to the top, which has a lower frequency. Just another now static slide showing you the same thing. High frequency, 4 hertz here. You're going to have 4 times as many peaks coming through in the same space as a 1 hertz wave, okay? So it's really important to remember all light travels at the same speed. That's this value C. It doesn't matter what the color of light is. It doesn't matter if it's radio waves, gamma rays, X-rays, microwaves, infrared light. All those are electromagnetic radiation, and they're all going at the same speed, okay? Here's another graphic showing you this. The different types of light are based upon their wavelengths. it's pretty remarkable. You know, we're using radio waves all the time, both for your radio, but also Wi-Fi and things like that. You're using very big wavelength light. We're talking on the order of meters, right? Up to, you know, hundreds of meters. These are huge waves, okay? And then, you know, something like visible light obviously is a lot smaller. We're talking about billions of meters. And when you get down to gamma rays, you have really high energy light, really short wavelengths down to 10 to the minus 13th meters, okay? So the way to think about this is that the speed of light is equal to your wavelength times your frequency. That's shown by this equation, C equals lambda times nu. And, you know, you can walk with long, powerful strides, okay? You're not taking as many steps, but you're gonna go the same speed as somebody who takes, you know, lots of small steps, right? They're traveling at a higher step frequency, but they could be traveling at the same speed as you, okay? And the combination of how fast you're actually going, i.e. C, right, the speed of light, is gonna depend upon how frequently you're taking steps, but then how big each of your step is, which is your wavelength, okay? And so that's pretty much it for this section. On the next video, we'll go over some calculations.